Okay, so what I discussed in the lecture last Tuesday, I discussed capacitors, inductors, okay, and then I discussed AC signals, and then I also had a discussion on complex numbers. So very quickly, just breeze through the material that I discussed. So una-una about capacitors, no? Actually, capacitors, I found out is a very misunderstood element. No? When I talk to students about capacitors, I realize that a lot of students don't really know the basics behind the capacitor. No? I mean, they know what it is functionally, but they don't really know the basics behind the capacitor. No? So yung capacitor, yung basic structure, okay, you have I won't draw the 3D anymore. No? This is the cross section. You have two plates, no? A top plate and a bottom plate. Of course, you have contacts. No? And then in between your two plates is a dielectric. So this is a conductor. This is also a conductor. And then this is an insulator. We call it a dielectric. Okay. Now, how does a capacitor work? Let's imagine we connect a DC voltage V across my capacitor. Okay, what will happen? Because this is positive, no? This is going to attract electrons. So meron tayong electron flow this way, no? Okay, because this is negative, this is going to repel electrons. No? So this is going to push electrons this way. No? Okay. So what will happen? Ano? Because electrons are flowing this way and electrons are being pushed this way, okay, pag nawala yung electron dito sa top plate na to, ito nagiging positive. Dahil yung electrons lumalabas. No? Dito naman, yung electrons natutulak this way. So pag natutulak dyan yung electrons, ito nagiging negative. So meron kang positive charges dito, meron kang negative charges dito. Okay. Now, while these positive charges are forming here and these negative charges are forming here, meron tayong current, no? And our direction of current is opposite the direction of flow of electrons. So the current will be this way, no? I, opposite the direction of flow of current. Okay. Now, what will happen, no? Meron kang positive charges dito, meron kang negative charges dyan, magkakaroon ka ng electric field. Okay. The electric field E will cause a potential difference to develop, no? Between the top plate and bottom plate. No? So magkakaroon ka ng potential difference between the top plate and the bottom plate. Okay, that potential difference will build up. No? Your current I, no? The electrons will stop moving, no? Or I will become zero. That is, the electrons will stop moving when the potential difference will be equal to V. No? So magbi-build up yung potential difference dito, magbi-build up yung potential difference between this and this. Okay? Now, when that potential difference equals this voltage, then your current I will become zero. So initially, may malaking current, no? Tapos unti-unting bababa yung current hanggang yung voltahe from the top to bottom will be equal to V. Okay. At steady state, that is, no, after it reaches equilibrium, I will be equal to zero. And that makes sense. Why? Because this is an insulator. The fact that that is an insulator, ibig sabihin, walang charges na pwedeng dumaan dyan. No? You cannot have charges flowing through an insulator. No? So if you think about it, kung walang charges na pwedeng dumaan dito, dapat itong I is equal to zero. And that is actually the case when your capacitor is at steady state and the DC and the excitation is DC. Ang tawag dito sa charges na to, this is your displaced charge. That is your displaced charge, no? And the displaced charge let's call that Q is proportional to V. No? The displaced charge, the charge that will be displaced is proportional to V. And the constant of proportionality is called your capacitance. In other words, Q is equal to CV, no? Where C is your capacitance. That is the constant of proportionality. Okay. Ang maganda sa capacitor, okay, sabihin na natin, no, nagkaroon na ng displaced charge dito. Tanggalin ko yung voltage. Let's say I remove now my voltage source. That electric field will continue to be there, and that displaced charge will continue to be there. So in effect, no, after I have displaced these charges, if I take out the voltage source, there is energy that is stored in my capacitor. And that energy is in the form of an electric field. And I can use that energy to energize other circuits if I now connect a load across my capacitor. Itong displaced charge, we call this the charge that is stored. No? Itong Q, this is what we call the stored charge. Okay? But in reality, there is really no stored charge. No? Kasi pag tinignan mo, if you take a look, what is the net charge inside this structure? Ano yung net charge? The net charge is equal to zero. Kasi kung ano man yung positive charges dito, yun din yung negative charges dito, no? Now when I talk to students, they seem to have this idea na dito sa loob, meron kang charges na nakatago when really there is no such thing. There's no such thing, no? What you really have is displaced charge. Okay? And then students also think that current can actually flow through the capacitor, but that is not true, no? Charges cannot flow through the capacitor. The reason why you have a current here is to create your displaced charge, no? And if this were AC instead of DC, ang nangyayari, nagbabalik-balik lang yung mga charges dito sa labas, ano? Because sometimes it's positive, so this is sometimes the polarity is positive, so this becomes positive. Sometimes the polarity is negative, so this becomes negative. Nagbabalik-balik lang yung charges, pero dito sa gitna wala naman talagang charge na dumadaan. Okay, so that's the principle behind your capacitor in a nutshell, no? And then you just review the equations related to the capacitor, no? Because if you have Q is equal to CV, no? If I get the derivative of both sides with respect to t, no, I'm going to get dq by dt is equal to c dv by dt, no? But dq by dt is equal to I, no? So my capacitor equation I is equal to c dv by dt. And note here, it's obvious that you only will get a current I if your voltage is changing with time. If your voltage is not changing with time, DC, for example, your current I is equal to zero, no? And if we manipulate this equation, you have V is equal to 1 over C, the integral of I dt. No? Where itong integral of I dt is actually equal to Q. Right? Because I is rate of flow of charges per second. So if you integrate I, you get Q. So this is your expression for V. Okay, and then P, which is equal to VI, that is just C V dV dt. Okay, if I yeah, voltage times current. If I multiply both sides of this equation by V, then I'm going to get VI is equal to C dV dt, which is equal to P. And energy, which is equal to the integral of P dt. Remember, P is the rate of doing work. So if you integrate that over time, that is the work done. Okay, this is just 1/2 CV squared. No? So those are your basic equations for your capacitor. Okay, punta naman tayo sa inductance. No? Inductance. Okay, ano yung inductance? Actually, you're going to see later on that the inductor is the dual of the capacitor. What if I have a coil? So, ginawa siguro nyo to science experiment ng grade school, no? Kukuha kayo ng pako, tapos mag-wind kayo ng wire around your nail. That becomes a coil. Okay? If you have a current flowing through your coil, I, what will happen? You're going to have a magnetic flux that will develop, and the concentration of the magnetic flux will be along the axis of your coil. So if I can show that here, okay, what will my magnetic flux look like? This is what my magnetic flux will look like. This is my magnetic flux. So this is magnetic flux. Actually, your magnetic flux, if you have a conductor, that's according to the right-hand rule. So for example, if this is your current, then you have a magnetic flux around your conductor based on the right-hand rule. But if you have a coil, okay, then the magnetic flux becomes parallel to the axis of the coil. Okay, and the magnetic flux, your magnetic flux will be equal to N times phi, where N is the number of turns and phi is the flux around a single conductor. Okay. Now N times phi is proportional to your current. N times phi, actually, sometimes you call this your flux linkage, but I don't want to introduce terms now. N times phi is proportional to your current. In fact, N phi is equal to Li, where this is now what we call inductance. And the unit for inductance is Henry. The unit for capacitance, by the way, I forgot to mention that earlier, is Farad. Okay, now, anong sinasabi ni Faraday? This is Faraday's law. Okay, if a time-varying flux is in the vicinity of a coil, okay, a voltage will be induced in the coil. Okay? So itong N phi, this N phi is in the vicinity of this coil, so magkakaroon ka ng voltage induced across this coil, no? So let's call that plus minus V. That is the voltage induced across the coil. And V, by Faraday's law, is equal to N dphi by dt. So dphi by dt is the rate at which the flux is varying, no? Remember, it has to be a time-varying flux. Kung hindi nagbabago yung flux, ibig sabihin wala kang voltage. So the flux has to be varying, no? Okay, if you get the derivative of this, no, both sides of this equation, okay, if I get the derivative of both sides of this equation, you're going to see that N dphi dt is equal to L di dt, no? Because N here is a constant and L here is also a constant, no? L here is also a constant. So N dphi dt is L di dt. So ano lumalabas, no? V is actually L di by dt. Okay. So that is your inductance equation. And notice that I has to be changing with time for there to be a voltage. Because if I is not changing with time, then your phi will also not change with time. In other words, if this is DC, kung DC ito, okay, what will be your voltage? Your voltage will be equal to 0. And that makes sense, ano? Kasi ano ba itong coil na to? Yung coil na yan, wire lang yan eh. That's just wire. Right? Wire is a perfect conductor. And therefore, if you do not have a changing flux, this just looks like a long short circuit. And the voltage across that will be equal to 0. Okay, so that is the nature of your inductance. Now, the thing about inductance, kung tatanggalin ko tong I na to, hindi basta-basta mawawala yung flux. Nandiyan pa rin yung flux. In other words, this will still be quote-unquote magnetized if all of a sudden I take I out. And therefore, I have energy that is stored in the form of a magnetic field. If I now put a load across my inductance after removing the current source, and if I put a load, okay, my inductance can now supply energy to that particular load. So that is the nature of your inductor. Okay, so if V is equal to L di dt, let's just try to develop the equations there. No, I will be equal to 1 over L, the integral of V dt. P, which is equal to VI, is now Li di dt. And then your energy, which is equal to the integral of P dt, is equal to 1/2 Li squared. So those are your inductance equations. So you have to remember your capacitance equations. So ito yung mga capacitance equations mo. And then you also have to remember your inductance equations. Okay, bakit hindi natin pinag-aralan yung capacitance at inductance when we did DC circuit analysis? No? So in DC circuit analysis, or let me be more specific, no, in steady state DC circuit analysis, okay, your capacitance is an open circuit. Your inductance is a short circuit. Okay. Inductance is a short circuit kasi kung DC, 0 yung di dt, so V is equal to 0, short, no? Your capacitance, I is equal to C dV dt, dV dt is 0, so I will be equal to 0, kaya open circuit. Kaya sa DC analysis, kung steady state DC analysis, again, no, steady state DC analysis, that is when the circuit is already in equilibrium, your capacitance and inductance are equivalent to either open or short, so nawawala siya. Ang natitira na lang yung resistor. That is why in the first part of the course, all of our DC analysis was just resistive networks because the inductances and capacitances disappear. Okay. Any questions? Any questions so far? So important, huh? Important that you understand the nature of inductance and capacitance. Okay, then we had a discussion of sinusoids. Ito, I'll just be very brief here. No? So a sinusoid is really just a signal, no? That takes the form of a sine or cosine function. No? Okay, so let's say this is f of t. Okay, you have f of m, you have fm. Fm is the amplitude of your sinusoid. That is the peak positive value. No, the peak positive value. Your sinusoid is symmetric with respect to the t-axis. Remember, this is your time axis. So that will also be the absolute value of your peak negative value. So your amplitude, okay, between your maximum points, this is t, and t is your period. Okay. If you get the reciprocal of t, 1 over t, okay, that is your frequency. Okay. 1 over t is your frequency. No? Your frequency is in cycles per second. Okay, your period is in seconds. Yung cycles per second, this is also called hertz. That's also called hertz. Okay. You have what you call your angular frequency. Your angular frequency is omega, which is equal to 2 pi times f. No? Every 2 pi, okay, is 1 period, right? So if you multiply 2 pi by f, this is going to give you your angular frequency, and this is in radians per second. That is in radians per second. So if you want to get the angle, no, your actual, well, let me put muna yan, no? Okay. This is what you call your phase angle. No? Let's call this phi. Phi is what you call your phase angle. No? This is the angle of your sinusoid at t equal to 0. Okay? Kasi dapat at t equal to 0, if this is a sine wave, if this is a sine function at t equal to 0, dapat 0 yung value ng sinusoid natin, no? But in this case, at t equal to 0, our sinusoid already has a particular value. So we say that the phase angle of this sinusoid, parang una na siya by this angle phi. And if you get a final expression for f of t will now be equal to f of m. Okay. In this particular case, sine, sine omega t plus phi. Okay. We could have expressed this as a cosine function. If we express this as a cosine function, mag-iiba tong phi na to. Kasi kung cosine function yan, then ang angle natin will be negative, ano? This will be the angle. No, sorry, it's still positive, no? It's still positive, sorry. Yeah, sorry. If this were expressed as a cosine function, the angle will be negative, no? So let's say this is theta. So you can also express f of t. This is f of m cosine omega t minus theta. Okay, omega t minus theta, where this is your theta now. Okay. Are there any questions? So that is your sinusoid, and the reason why we study sinusoids is, or why are we so interested in sinusoids? Okay, the natural output of generators are sinusoids. Okay. Kung meron tayong electric generator, dahil yung motion ng rotor ng generator is circular, it naturally produces sinusoids because of the circular motion. In other words, all our electric power are naturally sinusoidal. That is the electric power that is delivered in our houses, is our sinusoidal. And then in that lecture, I took up the concept of effective value. No? Effective value of a sinusoid. Okay, if f of t is equal to f of m, let's use cosine, no? Because from this point onward, ang magiging standard natin would be the cosine function. No? So let's say this is omega t plus phi. So gamitin natin yung phi. No? The effective value the effective value of f of t is equal to f of m over the square root of 2. Okay. Let me call that E effective. That's also sometimes called, that's F effective. That's also sometimes called FRMS. F effective or FRMS. F effective, this is the equivalent DC voltage that delivers the same amount of average power to a resistor as the sinusoid. So ang scenario natin is this, ano? Sabihin natin meron tayong sinusoid to. You have a resistor R. Okay. And then I have a DC voltage here. So this is F of t, no? I have a DC voltage here, F, I call it F effective, connected to the same resistor R. Okay. If F effective is the average power delivered by F of t to R, then F effective is the effective value of F of t. That is the effective value of F of t. Kung yung average power na dinideliver nito dito sa resistor R is equal to the power delivered by this to the resistor R, then this is the effective value of this. No? And you call it root mean squared, RMS. Yung RMS stands for root mean squared, because to get it, it is the square root. To get the effective value, it is the square root of the average of the square. The square root of the average of the square. If you try to do that mathematically, no, again, go to my lecture, no, andun sa lecture ko. But if you try to do that mathematically, you're going to see that ano ibig sabihin nitong root mean square. Okay. Okay. Final topic. Complex numbers. So your complex numbers, you have a real part plus an imaginary part. No? Natutunan naman to sa kahit sa high school, hindi ba? Yung what is an imaginary number? Can somebody answer me? What is an imaginary number?
Square root of -1, for example.
Yeah, square root of -1 no? Is an imaginary number. No? Sa high school, yung I is defined as the square root of -1. No? But in triple E, we use J instead of I. In other words, J is equal to square root of -1. And the reason why we use J, kasi baka malito tayo, no? Kung gamitin natin yung I, baka malito tayo na current yan, hindi constant, no? Hindi square root of -1. So ang ginagamit natin is J, no? So a complex number has a real part and an imaginary part, no? So for example, A, my complex number might be 2 plus J3. No? 2 plus J3. Ito yung real part, tsaka ito yung imaginary part. No? So this is your real part, and then this is your imaginary part. Okay. So yan, very very easy, no? Complex number, no? Ngayon, meron tayong tinatawag na polar form. No? A is equal to the magnitude of A at a certain angle theta. So for example, if I have 2 plus J3, this is call this my complex plane. Your complex plane is a Cartesian coordinate system. Yung vertical axis is your imaginary axis. And your we'll call that your imaginary axis, and your horizontal axis is your real axis. No? So let's say this is 2, this is 3. Itong point na to, this is 2 plus J3. So my imaginary axis 3, my real axis 2. That is 2 plus J3. So this is what we call your rectangular form. So meron tayong tinatawag na polar form. No? Yung polar form, yung haba nito, this is A. And yung theta is this. Okay? So my polar form for this, ano yung length ng A, no? Yung length ng A is just now going to be equal to the square root of 2 squared plus 3 squared, no? By Pythagorean theorem. And my angle, what is this? This theta is the arctangent of 3 divided by 2. So this is arctangent of 3 over 2. So those are your two forms. Any questions with regard to that? The two forms of your imaginary number. Actually, meron pang third form, no? The exponential form. But the exponential form is very close to your polar form, no? Your exponential form is A is equal to the magnitude of A e to the j theta. E to the j theta. Okay? Because by Euler's identity, I hope you know what Euler's identity is, or you've been introduced to it before. E to the j theta is equal to cosine theta plus j sine theta. Okay? And if you take a look at this diagram, okay, this is a cosine theta. No? And if you take a look, this is a, or this is JA sine theta. So actually, if I substitute this here, okay, I'm going to get my rectangular form. Babalik ako sa rectangular form because 2 is equal to this multiplied by the cosine of theta. And 3 is equal to this multiplied by the sine of theta. So ito yung third form, which we call the exponential form. And sometimes the exponential form is useful when you're doing mathematical manipulation. So what I want you to review with respect to complex number is review, okay, addition, subtraction, multiplication, and division of complex numbers. No? Why? From this point onward, you are going to be doing a lot of it. No? Ang mangyayari mula ngayon until the end of the semester, which is approximately 4 weeks from now, no? You actually have only 4 weeks to go. Apat na lang natitirang module sa inyo. No? This week, your introduction to AC systems, no, and then next week your phasor analysis. Then the week after power computations, and then the week after the transformers. Apat na lang. So including now, that's 4 weeks. And in those last 4 weeks, you're going to deal a lot with complex numbers. Now, why are we dealing with complex numbers? Because you're going to find that in the steady state analysis of AC circuits, we're going to use what is called the frequency domain analysis, or the phasor method. And that involves a lot of complex calculations. Huwag kayo matakot, no? It sounds intimidating, but once you get the use of it, once you get the hang of it, it actually isn't very difficult. And ang kagandahan ngayon, if you take a look at your calculators can actually manipulate complex numbers, basta they're already available as constants. Magagamit niyo yung calculator niyo to do these operations. No? The only time you cannot use your calculator is when you are multiplying, dividing, adding, or subtracting variables. And you have to write out the expressions for this. You have to be able to do this manually. Kasi hindi naman kaya ng calculator nyo na mag-iterate, for example, ng mga variables. Complex variables, rather. Okay. Any questions? No? And then I'm going now to go into an introduction of what I really wanted to introduce for today. Any questions? Okay. Magtanong na kayo if you have any questions. Okay, let me share now what I wanted to share today. Let's keep this. And here. Okay, introduction to phasors. Nakakatakot ba yung yung pangalan, phasors? It sounds like something coming out of Star Wars or Star Trek. introduction to phasors. What is a phasor? A phasor is a rotating vector in the complex plane. So what is my complex plane? That's what I showed earlier. No? My complex plane has an imaginary axis. This is my imaginary axis. And it has a real axis. So nakikita nyo yung real at saka imaginary dyan. I have a vector or a complex or a point that is rotating in the counterclockwise direction in the complex plane. Okay? And the angular frequency of rotation is omega radians per second. So yun yung bilis na pag-ikot nito, no? Omega radians per second. Okay. So if you take a look at the phasor, it has a real component and an imaginary component, both of which are time varying, no? Yung real component ko, ito yon, no? You notice this point down here, that is my real component, no? And then my imaginary component, hindi pinapakita dito, but that's this point, ano? This point. Okay, that's my imaginary component. Okay, so here, this figure, if I stretch this, so this is the trace, no? This is the trace with respect to time. If I create here a time axis, no? I create here a time axis, then this is actually what my signal will look like as a function of time. And take note that that is a sinusoid. Okay, so this sinusoid up here is how the real component of my phasor varies with time. Okay, now if we let A be a phasor whose angle with respect to the real axis is alpha at t equal to 0, the real component is given by A cosine omega t plus alpha. No? And that's very easy to see. No? If this is my imaginary axis and this is my real axis, let's say this is my phasor. Ito yung phasor ko. No? Let's call this A. Later on, I'll explain the convention, no? The convention for labeling a phasor. So at t equal to 0, ang angle that A makes with the real axis is equal to alpha. No? Now remember, this is rotating. This is rotating at omega. Sorry. But to be clear, no? This is rotating this way at omega. So after a time t, okay, this is going to be the position after time t. No? It would have moved, gagalaw siya ng omega t. Okay? Now, what is my real component? This is my real component. No? I can denote that as the real component of A. But what is this? Ano? This line is A, the magnitude of A, no? The magnitude of this cosine of, ano yung angle ngayon na to? No? This angle is just omega t plus alpha. Okay. So the real component is magnitude of A cosine omega t plus alpha, no? Which is consistent with this. So let's consider notation. So the phasor, this is my phasor. I can completely specify my phasor with just two quantities, my magnitude and my phase angle. So I already explained what the phase angle is. That's the angle the phasor makes with the real axis at t equal to 0. Omega is a third parameter of your phasor. No, that's the rate at which this is rotating. That is rotating around your complex plane. No? That's a third parameter, but that's an implied parameter. In fact, in AC circuit analysis, kung AC circuit analysis lang, omega does not change. For example, sa power nyo sa bahay, okay, your power in that Meralco supplies to you, your frequency is 60 hertz. Omega will not change. Omega, which is 2 pi f, will be approximately equal to 377 radians per second. No? So, for example, no, if 60 hertz, omega is equal to 377 radians per second. And this is in AC circuit analysis, that is a constant. That's not the same in, for example, in communications or in filters, because when you go to communication circuits or filter circuits or electronic circuits for that matter, pag minsan nagbabago yung omega. Because, for example, in communication, you might have different frequencies being transmitted simultaneously. So in that case, hindi na constant yung omega. But right now, most of the systems that we will be dealing with, constant yung omega. Okay. How do we differentiate between a phasor? Sorry. How do we differentiate between a phasor and a complex number? Kasi yung complex number, merong real part, may imaginary part. Yung phasor, meron ng real part and yung imaginary part. And it's very simple. Yung complex number is stationary in the complex plane, hindi gumagalaw. No? Whereas your phasor is rotating in the complex plane. No? Ngayon, para hindi tayo malito, dapat iba yung notation natin. No? So if you see this simple variable f, that is implied to be a complex number. Paano natin malalaman kung phasor yan? Paano natin malalaman kung umiikot yan? No? Pag nakita nyo itong j omega, f of j omega, then that is a phasor. No? Again, no? This is a complex number. It has a real part, an imaginary part, but it is stationary in the complex plane. This is a phasor. It is a real part, an imaginary part. No? It has a phase angle, but it is rotating in the complex plane. Alternative notation, pag minsan nakakatamad masyadong lagay itong j omega, maglalagay na lang tayo ng bar on top of the variable. No? Parang vector. It's like a vector. So this is an alternative notation that indicates that ito, f bar, is a phasor. Again, pag nakita nyo to, this is just a complex number. Pag nakita nyo to, this is a phasor. Okay? And I'm going to warn you. No? Hanggang dulo ng semester, I encounter students na hindi pa rin klaro sa ulo nila, no? What the difference is between a complex number and a phasor, because they are treated differently in your mathematical analysis. Okay, a phasor diagram is a snapshot of the phasor in the complex plane at time t equal to 0. So let's say these are both phasors. Okay, these are both phasors. Okay, at t equal to 0, the phase angle of phasor A is theta of A. At t equal to 0, the phase angle of phasor B is theta of B. So that's a snapshot. No? Kasi, again, no, imagine nyo, pareho itong umiikot, that is both turning. We take a picture at t equal to 0, and that is our phasor diagram. Okay, phasor transformation. I'll first discuss the rules for phasor transformation, and then later on I'm going to explain why we're interested in phasor transformation. So phasor transformation is the process of transforming a time domain sinusoidal signal into a phasor. In other words, meron akong sinusoidal signal expressed in the time domain, f of t. I want to transform that into a phasor expressed in the frequency domain. No? Ito ngayon ang tinatawag nating frequency domain, f of j omega. Now, this is the mathematical phasor transformation. If I have this time domain function and I transform that to a phasor, ito yung magiging itsura ng phasor. Okay. Take note that f of t, itong f of t, is the real component of f of j omega. I show that here. No? If this is my phasor, if I take the real component of that, in effect, that looks like f of t, no? A cosine omega t plus alpha. F of t is the real component of the phasor f of j omega. So what actually did we do? Ano yung ginawa natin when we converted this into a phasor? Ang ginawa natin, dinagdagan natin siya ng imaginary component. Kasi ito, this is just a real component. No? This is an actual sinusoidal function. This is composed of both a real component and an imaginary component. The real component of this is this. No? Yung imaginary component nito, dinagdag lang natin in the phasor transformation. Now, what will happen if this is a source in my circuit? What will happen if that is my DC source or my AC source in a circuit? Kapag ginawa ko siyang phasor, all of a sudden, magkakaroon ng imaginary component all over my circuit. No? So dati-dati, walang imaginary component, meron lang real component. Pag kinonvert ko yung source ko into a phasor, all of a sudden, I'm going to have imaginary components in all my voltages and currents in the circuit. And the reason for that is due to superposition. If I break this down into its two components, then remember by superposition, the resultant voltage or the resultant current will be the sum of the contributions of the different components of the input signal. So all my voltages and currents, because of superposition, will have both real components and imaginary components, or will be phasors. Now, what if I want to get the time domain response of the circuit from the phasor response? Then all I have to do is do the reverse transformation. I will do the reverse transformation. And what do you do in the reverse transformation? Tatanggalin mo lang yung imaginary component. You consider only the real component. Okay? Okay. Pasok siguro sa isip nyo. Bakit ko pinahihirapan yung sarili ko? No? Why am I making things hard for me? Why do I want to add an imaginary component before I analyze the circuit? Because exactly that's what's going to happen. No? What's going to happen when you analyze AC circuits now is, ang una mong gagawin, you convert your source to a phasor. In that process, you add an imaginary component, and then you analyze the circuit, and then after that, tatanggalin nyo yung imaginary component. Parang pinahirapan nyo yung buhay nyo, no? But actually, you're going to see that when you analyze circuits that way, the actual manipulation of your equations becomes very, very much easier. No? Because if you analyze in the time domain, you are dealing with differential equations. You recall earlier yung equations for your equations relating voltage and current in your inductance and your capacitance deals with derivatives. And therefore, when you put together your circuit equations, lumalabas differential equations. But when you use phasor transformation, the manipulations that you're going to do will all be algebraic. None of it will be differentiating or integrating. So that's the beauty of phasor transformation. Okay, in this particular course, and actually in electrical engineering, we're going to do a modified phasor transformation. So ito yung mathematical phasor transformation, ano? Ito yung sa math. This is math. But in electrical engineering, we modify this. Ang modification natin, inalagyan natin ng square root of 2 dito. So from my time domain to my frequency domain here, I divide everything by the square root of 2. And when I do my reverse transformation from frequency domain to time domain, binabalik ko yung square root of 2. And the reason why we do that, we introduce the square root of 2 so that when we are working in the complex domain, when we are working in the phasor domain, all the numbers that we deal with are RMS values or effective value. Kaya natin nilalagyan ng square root of 2. Okay. Now, this might confuse you, no? So there are two transformations we're talking about here. One is the standard transformation. No? Wala yung square root of 2. But in this course, we are going to do a modified transformation. Linalagyan natin ng square root of 2. And the reason why we do that, we want our values to be RMS values. Okay, so just some transformation examples. Let's see if you understood what I've been talking about. Okay, so ito. Can I have an answer? No? Can you transform this to a phasor? Anyone? Transform this to a phasor. Can I ask Joseph? Ano yung phasor equivalent ng F1 of T?
Hello? Hello po. Rinig po
Yes,
ako. Okay po.
Yes,
219.91 tapos yung angle po is yung 60 degrees.
Okay, that's right. Ano? Yan. F1, okay, by the way, no, dito usually we use a small letter because this is a time-varying quantity. Pag kinonvert natin sa phasor, usually we use a capital letter. No? So F1 of j omega is actually 220, no? Approximately 220, 219.9 at an angle of 60 degrees. Okay. And this is your RMS value of this, no? That is your RMS value of that. In other words, pag sinabi ng Meralco 220 volts, actually ang peak value nun is 311 volts. Eh. Pero ang sinasabi ng Meralco is your RMS value, which is 220 volts. Okay, so ang ginagamit natin ngayon is yung modified phasor transformation natin, no? Okay, what about this, no? Can I ask Albert, no? Ano yung reverse transformation nito? F of 2 of j omega.
Bali po, ano po, 14.14 cosine omega, cosine 377t plus 20 degrees.
Well, yeah. Okay, tama, no? That's assuming, kasi hindi ko naman sinabi ko ano yung angular frequency, no? But that's assuming omega is 377, no? But you're right, no? But kung hindi mo alam yung omega, kahit ilagay mo lang omega t, no? Plus 20 degrees. Okay, ngayon, itong third, this is a little trickier, no? Kasi this is sine. Okay? This is sine. So kapag yung sinusoid natin is sine, you have to convert it to its equivalent cosine. Right? So what do you use, no? You use your trigonometric identities that convert sine to cosine, no? So ang mangyayari is, okay, itong 377t minus 45 degrees, is actually equivalent, no, ito, no? Sine 370 minus 45 degrees is actually equivalent to cosine 370 minus 135 degrees. Okay, in other words, kung ano man yung angle nito, you have to subtract 90 degrees. Okay, because sine of theta is equal to cosine of theta minus 90 degrees. Okay? So ang magiging sagot natin dito, 100 divided by the square root of 2, that's 70.71 at an angle of mangyayari minus 45 minus 90 will be equal to minus 135 degrees. So warning lang yan, ano? That's because this is the sine function and not the cosine function. Our phasor transformation is defined with respect to the cosine function. Okay, I'm going to go through this very, very quickly. Ano? Okay, what if we now imagine our passive components, resistors, inductances, and capacitances, having phasor currents flowing through them. No? So let's say we have a resistor. Let's say this is my current, I of R. So it is specified in the time domain. Assume na lang natin that alpha or phi is equal to 0. No? Let's assume that phi is equal to 0. Okay, what if I, okay, from Ohm's law, V is equal to IR. No? V of R is equal to I R multiplied by R. No? And that's this. What if I now convert this to a phasor? No? Convert ko yung V of R to a phasor. Pag kinonvert ko to a phasor, so magiging V of R, j omega yan. So that's going to be this divided by the square root of 2 at an angle 0. No? That's going to be my phasor voltage. No? Now ito, if I convert this to a phasor, it's simple, no? Just Im over the square root of 2 at an angle 0. No? If I get the ratio of V over I, no, that will be equal to R. No? Now, I want you to park that thought, no? Because what we're going to try to do here is for the different components or for the different elements, we just want to get the ratio of the voltage over the current. No? So for a resistor, that will be equal to R. No? If I did that for an inductance, so let's say this is I of L, this is L. Okay, ito yung relationship ko between V and I in my inductor. So this was part of last week's lecture, which I touched upon again this morning. V is equal to L di dt. No? VL is equal to L di L dt. Okay, if I get di L dt, this is going to be my answer. No? Omega minus omega L Im sine omega t, I convert that to a cosine, ito yung magiging cosine equivalent niya. So let me convert this to a phasor. Let me convert V of L to a phasor. Ito yung phasor equivalent ng V of L doing a phasor transformation. Itong I of L, ito yung phasor equivalent, no? So yeah. Maybe just to make that a little bit clearer, no? So this is V of L. So ito, yung phasor niya is this, no? Ito yung phasor niya. Ito naman, yung phasor niya is this, no? And if I get, again, I get the ratio of V and I, ito yung magiging ratio. The ratio of V and I, if I divide this by this, if you know the rules of complex number division, so ito na, no? Pumapasok na yung complex number manipulation natin. No? If you know the rules of complex number division, okay, you're going to see that the result of that division is just this. That's why I asked you to review, no? Yung manipulation of complex numbers. And then gagawin ko rin yan with the capacitor. No? So from this, ito yung capacitor equation ko to determine V given I. Ito ngayon yung magiging evaluation nitong integral na to given I is this. No? Again, converting to phasors. No? So ito, kinonvert ko nito. Ito, that's this. Again, getting the ratio. Ito ngayon yung lumalabas na ratio. So the ratio of V over I is 1 over omega C at an angle minus 90 degrees. No? Pag yung angle natin is minus 90 degrees, ibig sabihin it's purely imaginary. Pag tinignan natin yan sa complex plane, no? Yung minus 90 degrees sa complex plane, so this is my imaginary, this is my real, andito siya, no? Okay, that is your angle is minus 90 degrees. So it's purely imaginary. By the way, no, sa inductor, your angle is 90 degrees. It's also purely imaginary, but on the other side, no? On the other side of the axis. Sa inductor, nandito siya. Sa capacitor, nandito siya sa baba. No? Okay, now that introduces now the concept of impedance. Impedance, if I have an element, and this can be an element, this can be a passive circuit. No? So either a passive circuit or an element. This is my phasor current, and this is my phasor voltage. If I get the ratio of voltage to current, then you call that your impedance, Z. That is your impedance, Z. So it's like a resistance, kasi resistance is the ratio of voltage to current, but resistance only applies to resistive DC circuits, no? Or resistive circuits. When it's now AC circuits, ang term na ginagamit natin is impedance. And in general, Z is a complex number. It has a real and an imaginary part, no? And we already know that for a resistor, I told you to park those ratios before. For a resistor, your impedance is equal to R. For an inductor, your impedance is J omega L. And for a capacitor, your impedance is negative J over omega C, or 1 over J omega C. No? Because 1 over J is equal to negative J. And that's mathematically, that's easy to show, because if I multiply this by J over J, J squared becomes negative 1. So those are the impedances of your resistance, your inductance, and your capacitance. No? And then the rest of these slides are just definitions. No? Reactance is the magnitude of the imaginary component of your impedance. So if I get the imaginary component of my impedance, that is just my reactance. No? Admittance is the ratio of current to voltage. Kumbaga, for resistive circuits, ito yung katumbas ng conductance. No? For resistive circuits, it's conductance. For AC circuits, it's admittance, the ratio of I to V. Again, in general, that is a complex number. For the resistor, your admittance is your conductance. For an inductor, it's 1 over J omega L. This is in Siemens. No? These are all in Siemens. And for a capacitance, it is J omega C. Again, definition, susceptance is now the magnitude of the imaginary component of admittance. So those are just a lot of definitions. So I'm going to stop there. Okay. So what did I introduce to you? No, I introduced to you what a phasor is, how you do a phasor transformation, So note what we are doing is a modified phasor transformation. It is not your mathematical phasor transformation, no? Because we modified it so that we are dealing with effective values. And then what is the ratio of phasor voltage to phasor current for any particular component? You call it your impedance. No? And then your reactance is the magnitude of the imaginary part of your impedance. The reciprocal of impedance is admittance, and your susceptance is the magnitude of the imaginary part of your susceptance. Okay, so that's it. No, I went rather fast, but hopefully, I don't know. You can go back to the recording and take a look at the material. So this is just supplemental again. What you should refer to is the official material in UVLE. This is just to supplement that. So take a look at that material also in UVLE. No? Okay. Any questions? Any questions?